Millions of years ago, a remarkable event unfolded in our solar system, one that scientists are only now beginning to piece together. A foreign star, possibly smaller than our Sun, made a dramatic flyby through our celestial neighborhood. This cosmic intruder came closer to the Sun than the Voyager probes are today, triggering gravitational upheavals that profoundly influenced the structure of our solar system. From reshaping the orbits of trans-Neptunian objects to influencing the peculiar retrograde moons of Jupiter and Saturn, this event left an indelible mark that still lingers. Recent research, including over 3,000 computer simulations, has unveiled stunning insights into how this stellar encounter might have occurred and its far-reaching consequences. To understand the significance of this event, we must first consider the Voyager probes, which represent humanity's furthest-reaching spacecraft. Launched in 1977, Voyager 1 and 2 were initially designed to explore the outer planets of our solar system. However, they have since ventured into interstellar space, with Voyager 1 now 24.6 billion kilometers and Voyager 2 about 20.6 billion kilometers from the Sun. While these probes are beacons of human ingenuity exploring the uncharted cosmos, new research suggests that a star once entered our solar system, cutting far closer to the Sun than these legendary spacecraft are now. This ancient stellar passage has profound implications for the moons of our solar system. When we examine the behavior of these natural satellites, a striking anomaly emerges. Some moons, like Earth's, follow prograde orbits, moving in the same direction as their host planets' rotation. However, Jupiter and Saturn harbor numerous moons with retrograde orbits, meaning they move in the opposite direction of their planet's spin. These retrograde moons often exhibit highly inclined and elliptical orbits, adding to their peculiar characteristics. For example, Jupiter has 71 retrograde moons compared to just 16 prograde ones. Similarly, Saturn's ratio of retrograde to prograde moons is an astonishing 100 to 22. For years, astronomers have puzzled over the origins of these retrograde moons. One prevailing theory posited that these moons did not form alongside their planets but were instead captured objects. Their origins were likely in the Kuiper Belt, a ring-shaped region beyond Neptune filled with icy bodies and the birthplace of many comets. According to this view, gravitational interactions caused these objects to be ejected from the Kuiper Belt and eventually captured by the gas giants. Jupiter's migration through the early solar system has long been considered a primary driver of these chaotic interactions. According to the Grand Tack model, Jupiter initially formed farther from the Sun and migrated inward, disrupting the primordial solar system in the process. This migration was later halted and reversed by the formation of Saturn, which stabilized Jupiter in its current orbit. During its inward journey, Jupiter's immense gravitational influence acted like a wrecking ball, scattering countless planetesimals, small building blocks of planets, and clearing the inner solar system. This violent reshuffling likely paved the way for the formation of the terrestrial planets, including Earth, while simultaneously setting the stage for the capture of retrograde moons. However, the Jupiter migration theory alone cannot fully explain the properties of these irregular moons, prompting scientists to seek alternative explanations. Enter the groundbreaking research by Suzanne Pfalzner and her colleagues from the Jülich Research Center in Germany and Leiden University in the Netherlands. Their study proposes that a close flyby of a foreign star offers a simpler and more comprehensive explanation for these phenomena. The team conducted over 3,000 computer simulations to model the potential effects of a stellar encounter on our solar system. Their findings, published in Nature Astronomy and the Astrophysical Journal Letters, suggest that a star approximately 0.8 times the mass of the Sun passed through the solar system at an angle of about 70 degrees to the planetary plane. This stellar visitor approached within 16.5 billion kilometers of the Sun, closer than the current distances of Voyager 1 and 2. Such a close encounter would have unleashed powerful gravitational forces, especially in the outer regions of the solar system. The simulations reveal that this stellar flyby could have flung many trans-Neptunian objects, TNOs, further into the depths of space while catapulting a significant percentage inward. Among these inward-moving objects, some were captured as moons by the gravitational pull of the gas giants, forming the irregular retrograde satellites we observe today. The numbers are staggering. Up to 7% of the trans-Neptunian population, potentially as many as 10 million objects larger than 100 kilometers and 10,000 objects exceeding 1,000 kilometers, were ejected inward during this event. The likelihood of these objects adopting retrograde orbits was significantly higher than prograde ones. In Jupiter's case, the probability of an object ending up in a retrograde orbit was about 30 times greater. This aligns closely with the observed ratio of retrograde to prograde moons around the gas giant. The implications of this research extend beyond the moons. The peculiar orbits of certain trans-Neptunian objects, such as Sedna, also find an explanation in this model. Discovered in 2003, Sedna follows a highly elliptical orbit that takes it as far as 17 astronomical units, AU, from the Sun. For reference, 1 AU is the average distance between the Earth and the Sun, approximately 150 million kilometers. The foreign star's gravitational influence could account for such eccentric orbits, as well as those of other distant objects with highly inclined or retrograde paths. This model not only explains the orbits of irregular moons and distant objects but also provides insight into the broader structure of our solar system. For instance, it sheds light on the sparse population of the Kuiper Belt. Falsner and her colleagues hypothesized that a stellar flyby around 4 billion years ago stripped much of the material from the primordial solar system's outer regions, reducing the Kuiper Belt's mass to just 1% of its original value. This near-catastrophic event may have been instrumental in shaping the solar system as we know it today. The beauty of this model lies in its simplicity and explanatory power. A single stellar encounter accounts for the irregular moons, the eccentric orbits of distant objects, and the diminished Kuiper Belt, all mysteries that have long puzzled astronomers. Moreover, it underscores the dynamic and interconnected nature of planetary systems, where even a brief stellar flyby can have profound and lasting consequences. This research also highlights the significance of our solar system's location within the Milky Way. Stars are not static entities. They move through the galaxy, often coming perilously close to one another. Such close encounters were more common in the early history of the galaxy, when stars were born in densely packed clusters. While the passage of a foreign star through our solar system is a rare event today, it was likely a more frequent occurrence during the chaotic formative years of our Sun and its planetary companions. The idea that our solar system's history has been shaped by external forces invites a broader perspective on cosmic evolution. It suggests that the solar system is not an isolated entity but part of a larger, dynamic galactic environment. Understanding these interactions can provide valuable insights into the formation and evolution of planetary systems across the universe. As scientists continue to unravel the mysteries of our solar system, the role of external influences like stellar flybys will likely become an increasingly important area of study. Such research not only enhances our understanding of our own cosmic backyard but also informs the search for life and habitable worlds in other star systems. The story of a foreign star's close encounter with our solar system is a reminder of the intricate and often chaotic processes that shape the cosmos. From the peculiar orbits of distant objects to the capture of irregular moons, this stellar visitor has left a legacy that continues to intrigue and inspire. As we gaze at the stars, we are reminded that the universe is a dynamic, ever-changing tapestry, woven together by the interplay of countless celestial forces. Millions of years ago, an extraordinary event occurred in our solar system, an event so impactful that its consequences are still observable today. A foreign star, likely smaller than our Sun, ventured dangerously close to the solar system, triggering gravitational chaos that altered the orbits of countless celestial objects. This stellar visitor likely influenced not only the peculiar orbits of trans-Neptunian objects but also the retrograde moons of Jupiter and Saturn. Recent research, backed by thousands of computer simulations, has provided a clearer picture of this dramatic event, revealing how it reshaped the solar system and continues to intrigue astronomers today. At Space Lab, we're dedicated to unraveling the mysteries of the cosmos and bringing the wonders of space closer to you. From groundbreaking discoveries to the most fascinating celestial events, our mission is to keep you informed and inspired. If you're as captivated by the universe as we are, make sure to subscribe and join our community of space enthusiasts. Together, let's explore the infinite possibilities of the cosmos, because at Space Lab, the journey to understanding the universe never ends.